So here I'll be solving the weight on a stick problem. As with all my physics problems, I like to draw out the physical situation in order to understand the problem better. Here we have a wall from which a stick is being suspended by a low weight cord. And hanging from the stick is a box. The box has mass m, as does the stick. The stick is 1 meter long, and the box hangs 0.75 meters away from the wall. There is some force of friction between the stick and the wall, F, and there's some tension in the cord, T. Between the cord and the stick, angle theta is formed. We are given that theta is equal to 20 degrees. The mass of the box and the stick are both 0.25 kilograms, and the distance from the wall that the box is hanging is 0.75 meters. We are also given that this system is in static equilibrium. What this means is that the sum of the forces acting on the system is zero, as is the sum of the torques. So let's begin this problem by writing out what we know. We know that the sum of the forces in the x direction will be equal to 0. The forces in the x direction are the horizontal component of the tension. Using basic trigonometry, we get this to be t times the cosine of theta, and we subtract that from the opposing force to that, which is the normal force of the wall on the stick. And we get that this value is equal to 0. Next, we know that the sum of the vertical forces is also equal to 0. The mass of the box is m, so we times that by the acceleration of gravity, g, which is 9.81 meters per second. And we add another mg because the stick has the same mass as the box. Now, if we subtract the upward forces, we have the upwards component of the tension, which using trigonometry we get to be t sine theta. And also there's the force of friction upwards, F. And these all sum together should be equal to 0. Using just a little bit of algebraic manipulation, we get that 2 times mg minus t sine theta is equal to F, the force of friction. So here we can clearly see that by solving for T, the tension in the cable, we can get the frictional force F between the wall and the stick. We do this by setting the sum of the torques equal to 0. As you may recall, torque is the cross product of a force crossed with the distance at which it is applied, which is equal to the force times the distance times the sine of theta, where theta is the angle between the force and the radius where it is being applied. So if we count downwards as positive, we see that the mass of the box acts at a distance of 0.75 meters away from the pivot, which we have set where the stick and the wall meet. So that accounts for 0.75 times the force, which is mg, times sine theta, which is 90 degrees because it makes a right angle with the stick. So sine of theta, 90 degrees, is just equal to 1. Then we add 0.5 times the mass of the stick times gravity for the force which is produced by the stick. And it's 0.5 because the stick is 1 meter long and the weight is evenly distributed, so the center of mass on the stick is halfway between. So here we also have the same situation where the sine of theta is just equal to 1 because another right angle is formed. Now, the opposing torque to this is the tension component, which is vertical. So here we see that tension acts a distance of 1 meter away, so we have minus t sine theta, because theta is the angle between the tension and the stick, and this should all be equal to 0. Now here, just through simple algebraic manipulation, we see that the tension is equal to 1.25 mg over sine theta. Plugging in the given values, we come across the fact that the tension force is 8.963 newtons. By plugging this tension back into the formula we derived earlier for the frictional force, we get that the friction is equal to 2 mg minus t times sine theta, and we get that the frictional force between the wall and the stick is 1.839 newtons. And that is how you solve the weight on a stick problem.